This video is about Riemann sums. We have been looking at finite sums that represent area under a curve, and these are very closely related. Those finite sums that we were looking at, those upper sums and lower sums, those are special cases of Riemann sums, but it turns out that there are lots of other Riemann sums that don't happen to be the upper sums and lower sums that we were talking about earlier. This video is about that Riemann sum and the definition of a definite integral, the relationship between a Riemann sum and a definite integral. But it's really about terminology. It's about what a Riemann sum is. It's less about calculation and more about understanding the concept. And so we're just going to focus on some definitions here. We'll do some very simple examples at the end that relate Riemann sums to definite integrals. And then in the next video, we will talk about what definite integrals represent in one important application geometrically as related to area. But this video is about Riemann sums, so let's get started. So this is our definition. It says, let f be a function defined on the interval from a to b. So there isn't much required of f. All it has to be is a function. And it's defined on the interval from a to b. It doesn't have to be continuous, nothing special going on there, it just has to be defined. Then we're going to let this delta, it looks like a little triangle, be a partition of that interval from a to b, given by this inequality. Now that looks kind of fancy, but there's not really nothing special going on there. X sub 0, that's just our a value. And we've got x sub 1, x sub 2, x sub 3, and so on. And then x sub n, that's our b value. So we started x sub 0, we ended x sub n. But now with this partition, we're not requiring all of those subintervals to be the same size, not with a Riemann sum. With a Riemann sum, the only requirement is that those x values are consecutive. So we've got x sub 0 here, and then x sub 1 is after that, and x sub 2 is after that, and x sub 3 is after that, x sub 4 is after that, and x sub 5, x sub 6, x sub 7. Eventually we get to x sub n. So they just have to be in the right order. And we start at A and we end at B. But the interval from x sub 0 to x sub 1 doesn't have to be the same size as the interval from x sub 1 to x sub 2 anymore. And then we're going to let delta x sub I be the width of that ith subinterval. Now, notice that the first subinterval goes from x sub 0 to x sub 1. And the second subinterval goes from x sub 1 to x sub 2. So the ith subinterval always ends with x sub I. So the third one goes from x sub 2 to x sub 3. So that's why it says the ith subinterval ends at x sub I. So if it's the third, that's going to end at x sub 3. And then this is just the x value before that. So if this is x sub 3, that would be x sub 2. If that's x sub 5, that's x sub 4, and so on. So that's the width of the ith subinterval. Then if x sub I star is any point on that subinterval, so I'm on the interval from x sub 1 to x sub 2, I pick any x value I want. That's on the second subinterval, so I'll call that x sub 2 star. If I evaluate my function there, and then make a little rectangle that extends from x sub 1 to x sub 2, that approximates the area under the curve on that interval. And I'll do the same thing on the interval from x sub 0 to x sub 1. Pick an x value, evaluate the function there, and draw a rectangle. And we do one over here, and then over here, pick some x value on the interval, make a rectangle. Pick some x value on the interval, make a rectangle. You could pick the left endpoint or the right endpoint or the midpoint or any x value in between. Any x value you want, that's what x sub I star is. Any x value on that interval. Okay. And if you find the area of all of those rectangles, even though they have different widths, each rectangle, and you add them together, that's called the Riemann sum of f for that particular partition. Okay, now we've got some more terminology. The norm of the partition is denoted by this, and it's a width. It's the width of the largest subinterval of the partition. Since it's a width, it's always greater than or equal to 0. Well, I guess it's going to be greater than 0, isn't it? It has to, x sub 1 and x sub 2 are never the same. So I guess, let me change that. It's strictly greater than 0 because x sub 1 and x sub 2 are not the same. Now, a regular partition are the types of partitions that we were looking at in the last few videos. In a regular partition, every subinterval has the same size or the same width. So in a regular partition, we usually denote that width by delta x, and we just take b minus a, and we divide it into n equal pieces. And when we do that, all of the rectangles have the same width, delta x. Now, in general, for a general partition, the norm of the partition, which is the width of the largest subinterval, which happens to be delta x for your regular partition, satisfies this relationship. N is the number of rectangles that you're drawing. This is the width of the largest subinterval. And b minus a over that width is always less than or equal to n. Now this doesn't tell me much, but if I write it this way, if I multiply both sides by this positive width, I get this. This actually makes sense to me. This is saying that the length of that interval from a to b, which is b minus a, if that was 10 and that was 4, that length would be 6. I would just do 10 minus 4 to get that length of 6. Well, that length has to be less than or equal to the number of rectangles, or alternatively, the number of subintervals times the width of the largest subinterval. So if all the subintervals are the same size, so that this would be delta x, I'll have b minus a over n times n, and I get b minus a equals b minus a. If they're the same size, that's true. But if some of them are larger than others, if I take that largest one and I multiply it by n, well, then I'm going to get a number that's larger than that subinterval. If I took this and I multiplied it by n, well, that's going to be much larger than the total width of all of those subintervals, or the total width of this interval from a to b. So this actually makes a lot of sense. Now, since this relationship is true, if I take both sides and I divide it by the norm of the partition, that's the width of the largest subinterval, look what happens to this relationship. If the width of that largest subinterval approaches 0, so I'm looking at the norm of my partition, I'm looking at that width, and that's getting smaller and smaller. Oh, this is a positive number, generally, divided by a tiny positive number. A positive over a tiny positive number is going to be a large positive number. N always has to be greater than or equal to that. So if this 0 over a tiny positive number is large, and it's getting larger and larger as that denominator gets smaller and smaller, this fraction is going to infinity, and this has to be greater than or equal to that. So as the norm of the partition approaches 0, the number of rectangles has to go to infinity, because this inequality is true, because it holds true. We're guaranteed that if this goes to 0, n goes to infinity. Now, in general, letting n go to infinity does not necessarily imply that the width of the subintervals approaches 0. Maybe I've got infinitely many subintervals, but maybe there's one at the beginning, and I've got this big area here, and then I've got infinitely many over here. Well, if I'm approximating area under the curve with something like this, well, I'm always going to be a little bit wrong because of that first subinterval that didn't go to 0. Even if I have infinitely many pieces, and I'm going from the interval from a to b like this, even if I have infinitely many pieces over here, if one of those subintervals is staying finite, so that width is not approaching 0, then we're not necessarily guaranteed to find that area under the curve that we've been talking about. So anyway, for a general partition, this is true, And that means that as the norm of the partition approaches 0, so that's as that width, that delta x sub I, for all of the delta x sub I, for all the i's, as that goes to 0, every single one of them has to approach 0, well then the number of rectangles goes to infinity. And as I was trying to explain, that it doesn't work the other way. Letting n go to infinity does not guarantee that the norm of the partition goes to 0. Now, if we have a regular partition, like the partitions we've been talking about with our upper and lower sums, as n goes to infinity, delta x does go to 0. So that works. This is a special case of a Riemann sum, because as n goes to infinity here, delta x goes to 0, and if delta x goes to 0, well, it's a special case of a limit of a Riemann sum, which we're going to talk about in a little bit. But my point is, for a general partition, letting that width go to 0 implies that the number of rectangles goes to infinity. But in general, it doesn't always work the other way around. It does happen to work the other way around if the subintervals are exactly the same size, delta x. Okay, it's a lot of terminology. Watch this video again if you're not sure, and of course, you're welcome to ask me questions. Okay, so now let's talk about what a definite integral is. So let's say f is a function that's defined on the interval from a to b, and the limit of Riemann sums over all the partitions, delta exists, so that if the norm of the partition goes to 0, then you can take the limit of this as the norm of the partition goes to 0 and you get a finite number. If that works, then we say that the function f is integrable on the interval from a to b, and this is equal to this. Now this is the notation we tend to use, but this means this. This is called the definite integral of f from x equals a to x equals b. Notice it looks just like our antiderivative notation. Now you just have a little number here and a little number here. A is called the lower limit of integration. And b is called the upper limit of integration. So what were we saying? We're saying that if we create this sum, so we take our interval from a to b, we subdivide it. We evaluate the function at a point on every subinterval. We find that value and we multiply by the width of that interval. So we get this. I forgot my little I. So you're getting areas of rectangles provided that that function lies above the x-axis. If the limit of this as the norm of the partition goes to 0, which means that all of those delta x sub I go to 0. So that means there's not any rectangle that just sort of stays wide. They all get very, very, very small, infinitely thin, so thin, we're going to write a dx here. Then we say that the function is integrable, and this limit is defined to be this definite integral. Okay, now notice the similarity between antiderivatives. These are sometimes called indefinite integrals and definite integrals, but also notice the difference. Here I've got a number a and I've got a number b. Over here there are no numbers. Here I'm finding a function. Actually, I'm finding a family of functions. And remember what that family tends to look like. We typically use capital F of x plus c. If I take the derivative of this, I get little f back. And of course, the derivative of the constant is always 0. This is different. This is very different. The notation is the same because it turns out these two are related, but this is a very different beast. This gives me a family of functions. This over here is found this way. So what do? We found heights of rectangles. We multiplied by delta x. We added those together. Those are all numbers. I'm taking all those numbers and I'm adding those together as I goes from 1 to n. And then I'm saying, what happens to that as all of those delta x sub I, forgot to put my I there, as all of those delta x sub I go to 0? Does that always approach the same thing? If it does, if it always approaches the same thing as the norm of the partition approaches 0, well then this is what it approaches. It approaches this. So this is a number. This is a family of functions. So these are two very different things. And this finite number can represent area, it can represent arc length, it can represent surface area, and we're going to look at all of those things in calculus too. But for right now, I just want you to know a definite integral gives a finite number, an indefinite integral gives a family of functions. Now, the next theorem is something that comes very much in handy. It says that continuity implies integrability. So if our function is continuous on the interval from a to b, and most of the time the functions that we're looking at in this class are continuous, then that limit will exist. So you should be able to do this, and it'll work for every partition. So this limit always exists, and you're going to be able to evaluate this integral, and it's going to represent, or it's going to have some value, and that value will be a finite number. And that's what we mean when we say the function's integrable. It means you can do this for all the partitions, and as long as the norm of the partition goes to 0, you're going to get this. Okay. You might have to watch this again. That was a lot of terminology. But the idea is just that you would understand that those finite sums that we were looking at in the other videos, where we were looking at all of those widths being exactly the same size. And we said if the function is positive, this represents area. And we said all of those things. Those were just a very special case of something much more general. And that much more general limit is what defines this definite integral over here. Okay. And if the function's continuous, it's integrable, and that's going to be nice. It's going to come in handy for us. So we're only going to do a couple of examples in this video. And our goal is just to write each of these limits as a definite integral. So what you want to do is basically say, okay, I see the limit as the norm of the partition goes to 0. So that's that delta x sub I. That means all of those go to 0. Of this sum on the interval from x equals 0 to x equals 3, well, that will represent a definite integral provided this limit exists. And the corresponding function here is continuous, so it does exist. So let's write it down. This is equal to this definite integral. Since I'm given this interval, this is my a and this is my b. So I start at 0 and I go to 3. And this is f of x sub I star. Now our textbook uses c sub I. I use x sub I star because that's the way I was taught. We're using x sub I for the endpoints of each subinterval. But that's beside the point. In the book, when they use c sub I, we're just using x sub I star in our notes. So this is a and this is b. If this is f of x sub I star, look at the notation. You're supposed to write f of x there times dx. So this little delta x sub I is going to become dx in the limit, or that's how I tend to think of it. It becomes infinitely small, so we call it dx. And then this over here, I'm just going to write in exactly the same thing, but instead of an x sub I star, I just write x, because we're evaluating f at x instead of x sub I star. So this is x squared plus 4 all raised to the 1/2 power. That's all that is. Okay, this is similar. This represents a definite integral as well. I've got the limit as the norm of the partition approaches 0 of this on the interval from 0 to pi. A is 0, b is pi, so we're integrating from 0 to pi. And then this is f of x sub I star. So you just replace all the x sub I stars with x's. So I see e to the x sub I star, that's going to become an e to the x. And then I see sine of x sub I star, that just becomes a sine of x. And then in the limit, this delta x sub I, that's the width of that I subinterval, becomes infinitely small. I'm going to call it dx. And that's it. This over here is equal to that over there on the interval from 0 to 3. And then this over here is equal to that over there on the interval from 0 to pi. So this is the definite integral that's represented by this limit. In the next video, we'll talk about what these represent geometrically. It's related to area, as you can imagine. And then we'll talk about some properties of these, and we will evaluate some definite integrals.